So how does moon create tides on the Earth? Right? In the absence of any tidal interaction by the moon, the Earth is like almost like a sphere. But because of the tidal interaction, the Earth gets deformed as an ellipse, right, or ellipsoid. So the gravitational waves does something similar to that. So if a gravitational wave is passing perpendicular to this whiteboard, the space gets stretched in the orthogonal direction, like this. At the same time, it gets compressed to the other direction. So, and both orthogonal directions are perpendicular to the direction of propagation. So they are transverse waves. Now, imagine what would happen if we have a ring of, let's say, free particles that are free to move. Then if you have a ring of particles, because the space is stretched in one direction and compressed in the other direction, this ring, the circle, gets deformed into ellipse. And this is similar to what happens to the Earth by the tidal interaction of the moon. So this is a cartoon that shows what happens to a ring of test particles, which are free to move, when the gravitational wave is passing in this direction. So you can, if you focus on one particular ring, you see this is a circle that gets elongated in an ellipse in this direction, and the next half cycle, this comes back, and the orthogonal direction gets stretched, and the sort of these y direction get compressed. So this particular deformations can be very easily detected, well, not very easily, in principle detected using an interferometer. So I guess most of you study an interferometer in college. So this is a schematic diagram of a simple interferometer. So you have a beam splitter that is splitting the light from a laser source into two orthogonal directions, and you have two N mirrors that reflect the light backwards and forming an interference pattern here. And initially you can adjust the length of this interferometer, this amps, in such a way that this interference is destructive, so that no light is leaked from this what is called dark spot. And when a gravitational wave pass perpendicular to this interferometer, the space in one direction gets stretched and the other direction gets compressed. As a result, this arm gets slightly longer and this arm gets slightly shorter, which will introduce a relative change in the path length between two arms, which will get converted into a phase difference, and the interference pattern changes. So this initial dark fringe becomes a bright fringe, and you can actually record this change in the brightness of this original dark spot using a photodetector and record that. That's how a gravitational wave detector works. So interferometry is a very standard technique. It's more than 100 years old. But the challenge is that the expected change due to the passage of a gravitational wave is extremely tiny. For example, if you look at the fractional change of like delta L to the original length of the interferometer L, even if you have a very loud gravitational wave that is being detected by LIGO at this point, this fractional change is of the order of 10 to the power 21. So which means that if you use a tabletop interferometer of 1 meter length, the length change produced by the passage of a gravitational wave is of the order of 10 to the minus 21 meter. Even if you have a kilometer scale instrument, the actual change, delta L, is of the order of 10 to the minus 18 meter. That's of course much smaller than the wavelength of the light itself, and in fact this is like 1,000 times smaller than the size of a proton. It's a very difficult measurement problem, and that's why it took so long to detect gravitational waves, even though people were fairly confident that gravitational waves existed for the last 50 years or so. So several international groups have made this big observatories of gravitational waves that are used that make use of the principle of laser interferometry. These are the aerial photographs of the LIGO observatories in the USA. These are L-shaped Michelson interferometers of 4 kilometer arm length. And there are two of them, the two corners of the United States. They are separated by about 3,000 kilometers. And in fact, the LIGO observatories have been functioning over the last decade or so, although with a reduced sensitivity. And what has happened in the last 3 years is that they went through a major upgrade called the advanced LIGO, which improved their sensitivity as compared to the previous generation by a factor of 3 to 4. And as soon as they started operating in 2015 September, they observed the first gravitational wave signal. So let me show you a picture of the first observed signal. This is the time axis, and you can see it's a very short signal, so for a fraction of a second, like 0.1 second or so. And this is these two signals shows the actual time series of the signal that is observed by the LIGO observatories. There are two of them, the LIGO Hanford and the LIGO Livingston in the two corners of the US. And on top of that, it also shows the frequency evolution signal. So do a simple spectrogram that shows that how the frequency of the signal is evolving as a function of time. So you can see that this signal, the frequency is steadily increasing until then abruptly stops. So this is a classic signature of what is called a chirping signal, where the frequency and the amplitude of signal is increasing as a function of time. This is, for example, this is how the chirping of birds sound like. And this chirping signals are expected to be produced by the in spiral of binary systems of two stars. So you have two stars which are extremely compact and massive. They could be black holes or neutron stars. They're not normal stars, they're dead stars. And they orbit each other and with very high velocities, producing gravitational waves. And because the system is losing energy, they would come closer and closer. And when they come closer and closer, because of the conservation of angular momentum, or Kepler's third law, they would orbit faster and faster. And the frequency of this orbital motion would increase as a function of time, which is what you see in the signal itself. Because the gravitational waves, basically, the frequency of gravitational waves is just twice the orbital frequency. Until they coalesce, they merge to each other, producing a loud burst of gravitational waves. So, this is, of course, the very first signal that LIGO was detected. But in the last 3 years, during the first two observing runs of LIGO and Virgo, the European counterpart of LIGO, these observatories have detected 10 binary black hole coalescences. So this shows the distribution of the masses of these black holes that LIGO and Virgo have observed. This horizontal axis is the mass of this object in the binary system in the units of mass of the sun. So here is the two solar masses, the mass of the sun, two solar masses, 5 solar mass, 10, 20, 30, so 40, 80, etc. So, and as you can imagine, a binary system consisting of two black holes that their masses are shown here and here, and eventually they would spiral in and merge with each other, producing a more massive black hole, which is shown here. So this is sort of it's a cartoon of all the masses of the black hole that LIGO has observed during the first two observing runs. There are 10 of them. And you can see that these are, on average, they have masses of the order of 20 to 30 solar masses. They are all black holes. We believe that they are all black holes because they are all consistent with what we expect of a signal from binary black hole systems. And of course, this is not the first time we are seeing black holes through astronomical observations. There has been a number of X-ray observations from our own galaxy which uncovered the existence of black holes. But it turns out that all these black hole candidates that X-ray astronomy has produced have masses of the order of 10 solar mass. They're shown by these slightly purple spots here. And it turns out that the LIGO, so the LIGO observations are uncovering a different population of black holes that were not to exist until, it was not to exist until LIGO made these observations. So until recently, most of the astronomers were believing that black holes would be of the order of 10 solar mass. But until now, with these LIGO observations, we are uncovering a new population of black holes, which are of the order of 30 times the mass of the sun, and even more massive. The new observations are slowly uncovering. Of course, this is the this is of course the results from only the first two observations, first two observing runs, And the LIGO and Virgo have been conducting a third observing run starting from April this year. And they have been observing binary black hole signals with almost weekly rates. So there are several tens of binary black hole observations have been made the last few months, apart from a couple of binary neutron star observations and binaries consisting of a black hole and neutron star. So this plot is getting very busy over the last.
How many light years are
they are billions of light years away.
so presently they may not be existing at all.
That's right, yeah. Well, we expect this final remnant to exist. The merged black hole would exist, but this binary system have collapsed a long time before. Yeah, that's a good question. These are all really cosmological distances. They are coming from hundreds of megaparsecs or billions of light years, which means that when these collisions happened, life was in a very primitive form on the Earth. So all these billions of years, these signals have been traveling through the space and finally reached us this year or last year, etc. It also means that this collisions of binary black holes is a fairly common phenomena that happens in a galaxy every million years, something like that. So these, apart from the first direct detection of gravitation waves, these are the first detections of merging binaries of black holes, because black holes by definition do not emit any light. And so far, we have been detecting the presence of black holes by the motion of luminous objects, the stars around the black holes, or motion of accretion disks, which are again luminous objects around black holes. But if you have two black holes which are by definition black, there is no way of observing them through electromagnetic